Hello. Previously we derived the collisionless Boltzmann equation or the Vlasov's equation and also collisional Boltzmann equation, which is mostly called the Boltzmann equation simply. Okay. And if you remember the form, we said that the collisionless Boltzmann equation should look like this. Where f is the kinetic distribution function, right, and which can be a function of the position, the velocity and time. Okay. And so, the equation should look like del f del t plus u dot nabla of f plus f by m dot nabla in the velocity space or the gradient in the velocity space of f. Okay. And u is the kinetic velocity, f is the body force, okay, and m is the mass of the particle of one particle. Okay. And then we also derived the collisional form of this, where this right hand side was not equal to 0. So, that was the collisionless form, and for collisional form we had this integral which we call the collision integral, okay. So, where f prime, f1 prime, f1, they are just the distribution functions of, so, r u prime t, and here the other two things are kept unchanged, r and t. This will be just replaced by r u 1 prime t, it was r u t, and this one was function of r u 1 t. Okay. This is true, this collision integral is valid when we were considering binary collisions of two particles. Okay. So, they collided, and before collision they had velocities u and u1, and after collision they had velocities u prime and u1 prime. Okay. So, this was only model for binary collisions, elastic in nature. So, binary elastic collisions should be there, and then only we can model the effect of the collision, or rather this is the this is the net, okay, this is the net change in the. So, if you remember this one, this is nothing but df dt. So, this is, okay, if you just follow one trajectory of evolution in the phase space. So, the time rate of change of the distribution function will be exactly equal to this one. Okay. So, this model is not a general model for any arbitrary collision, it is for a very simplistic case, right. Now, using this integral, we now want to fetch some information about the nature of the f, that means the nature of the distribution function for a gas or a classical system of particles, okay, which are left for long time, okay. And we will see that towards which distribution the system tends to relax itself, okay. And that we will call the equilibrium distribution function, equilibrium distribution function of the system F0, okay. Now, one thing I have to mention here, if you remember here I just changed in this 4 terms involving the distribution function, I only changed the u's, okay. Here u prime, u1 prime, u and u prime, but I did not change r. That was because the collisions were assumed to take at one point in space. So, just before and after the collision no change in position or no considerable change in position took place, okay. That was the assumption. Now, we will try to formulate F0, okay. Let us consider how to know the functional form of it, okay. Let us assume a gas, a classical gas, or rather an ensemble of molecules. Here I am not talking about the ensemble at phase space, but ensemble of molecules means just a collection of molecules, okay. Classical molecules which are interacting within themselves, okay, just by in terms of elastic binary collisions, okay. And then we just let it evolve without any force or anything, okay. So, the system is just left to evolve freely, and then we will try to understand what is the distribution function for that. Now, Maxwell in the year 1860 he already pointed out that such a classical gas, if it is uniform or homogeneous, that means the density of the gas is equal at every point in space. So, for a uniform classical gas, F0 should be a Maxwellian distribution. Okay. Now, what is that and how to really show that? That exactly we will do here. Okay. So, here we will try to do this directly from our collisional Boltzmann equation. So, collisional Boltzmann equation will give us del F del T plus u dot gradient of F plus A. A I just write the acceleration which is F by m, okay, dot the velocity space gradient acting over F is equal to the collision integral. This is the collision integral, okay, the whole integral. Now, we have to construct by using step by step assumptions the form of F0, okay. So, if this is true for all F, then of course, this is also true for F0, okay, it is true. Now, one thing we have to understand that if the gas is left for long time, then if it will tend towards an F which is equal to F0, that F0 should be independent of time, okay, should not explicitly depend on time, okay. That is why we can write del F0 del T will be equal to 0, that is somehow reasonable, okay. So, because when the system is left for long time, then the system is expected to attain a steady state. So, all the properties including the very basic distribution function should not be a function of time then, right. The system will always try to tend to the equilibrium, and when it attains the equilibrium point, then it will hardly change with time. This is the concept behind it. And again we can say that the equilibrium distribution function is also independent of R. That means gradient of f0 is also 0. Okay. So, it simply says that if, let us say, if f0 is a function of R, then you all know now that when if f0 is just integrated in the velocity space, then it will give us density, and if there is a R dependence, then when it is integrated over velocity space, here it will have also an R dependence. That means, uniform gas will no longer be uniform, right. So, for any uniform gas, so basically here you do not need to wait for long time, you just say my gas is homogeneous or uniform, then the density should be a constant, right, and it should be uniform everywhere in the space, right. And then of course, this thing is that this type of R dependence should not be there. Okay. So, this will be the thing. So, the only dependence should come from the velocity, then f0 will be simply a function of velocity. That much we can conclude till now. Okay. Now, if you see that the left hand side of the whole equation, okay, whole collisional Boltzmann equation, this term is vanishing, this term is vanishing because gradient of f is 0, and what about this term, is this also vanishing? Well, when we are talking about equilibrium, at equilibrium A or f by m is 0, because equilibrium is assumed from mechanical consideration a state where you have 0 force. So, it is a force free state. Okay. So, the third term is also 0 because f is 0 there. Okay. I can actually even reason from here. So, this one is 0, this one is 0, this one is 0. So, the whole left hand side is 0. So, the right hand side should also be identically 0. So, the collision integral should identically vanish at equilibrium. Okay. So, we can simply write d cube u1 integration sigma of omega u minus u1 within bracket f0 prime f01 prime minus f0 So, I have just replaced every f by its f0 value, okay, because we are talking about equilibrium. So, this will be the new thing, and then it is integrated over this is identically 0, and this is true for any arbitrary choice of u1 omega. So, the only condition by which it can be true is that f0 prime f01 prime should be exactly equal to f0 f01. That means that the integrand itself should vanish. Okay. So, you see you have the product of two equilibrium distribution functions before and after the collisions are unchanged. Okay. And then if you take the natural logarithm, you can say log of f 0 prime plus log of f 0 1 prime is equal to log of f 0 plus log of f 0 1. So, you see that this is simply like something, I mean when you talk about the momentum conservation or energy conservation before and after the collision, let us say the particles are of equal mass m, then for example for momentum conservation you say let us say for x component conservation, right. You say u prime x plus u 1 prime x is equal to u x plus u 1 x, right. This type of thing we write, okay, for momentum conservation. So, here this is the actually the it looks that this analogous thing, right, over here. So, log of this f 0, so log of f 0 is a quantity which is conserved in a collision, of course, which are binary and elastic in nature, because otherwise this collision integral form will not be the same. Now, you also know that log of f 0 is a function of u, because f 0 is a function of u. So, log of f 0 is a function of u. Now, we will do a trick. So, is conserved in collision. Of course, we know which type of collision, so nothing new here. Okay. Now, we will do a trick. Let us now assume that some function chi r, which is a function of the u velocity, okay, vectorially, is conserved if in a collision and if we find n number of such conserved quantity okay. You have this, okay, and where all of them are function of velocity in general, and the chi r's are, now there is an important thing, mutually independent. That means they are independently conserved. One conservation does not depend on the conservation of the other. For example, if you are considering the conservation of momentum, okay, you can think the three components of the momentum, okay, will be conserved in a collision separately or individually, right. So, the three components they are conserved being independent of each other, and there is another independent conservation is there, which is also a pure function of velocity, that is the kinetic energy, right. There is another conservation which we do not talk in general, that is the conservation of number, right. So, the number of the particles they are also conserved before and after the collision. Then if you just put u to the power 0 over there, okay, then you will see that 1 plus 1 will be equal to 1 plus 1. So, 2 particles will be 2 particles. Okay. So, now all this the number conservation, the conservation of the momenta, the linear momentum, the conservation of component wise of course, and finally, the conservation of kinetic energy, all are the mutually independent conserved quantities in a collision. We can finally write log of Fu, okay, which is a conserved quantity of collision, as a linear combination of all these conservations. Okay. Of course, here we are just assuming that we have found all the conserved quantities. So, basically chi r, they will form a basis, okay, and any arbitrary conserved quantity in an elastic binary collision will then be expressible in terms of this. So, the C0 can be absorbed inside the summation, and then you have to just write r is running from 0 to n and chi 0 should be just 1. Okay. So, in this way you can write the whole thing. Now, assume that in case of simple mechanics, okay, microscopic theory in a classical framework, we only have the conservation of number, conservation of the 3 components of linear momenta, and conservation of the kinetic energy, okay, and that forms the, that completes the basis. Okay. We do not have any other conserved quantities. If we assume that, okay, then we can write for our case log of Fu should be equal to C0 plus C1 u square. So, this is the form coming representing the kinetic energy conservation. Then 3 components are conserved individually for the linear momenta, and I am just writing this. Okay. All the C0, C1, C2x, C2y, C2z, they are all constants. Okay. If we can write this, then by a little manipulation we can also write log of Fu will be simply equal to minus b u minus u0 whole square plus natural logarithm of e, where you can easily express b u0 and a in terms of C0, C1, C2x, C2y and C2z. I can do the first one. So, if you just write this thing like minus b u minus u0 square plus ln a, you have to write this equal to C0 plus C1 u square plus C2x ux plus C2y uy plus C2z uz. Okay. Just by matching the powers of u in both sides, you can simply say that b is equal to minus C1. That is the first thing. Okay. That you can easily see from matching, by matching the powers of u square. So, that will be C1 and here that will be just minus b. So, b will be minus C1. Okay. Then you can also say minus b u0 square plus log a is equal to C0, but here you have one unknown is known now. So, it is expressed in terms of C1. Now, you have 2 other unknowns, unknown constants u0 and a. Okay. So, but you have other conditions as well, 2b u0 x is equal to C2x, okay, 2b u0y C2y and 2b u0z is equal to C2z. Okay. If you combine all, you can actually see that you can simply say that my u0 square is nothing but u0 x square plus u0 y square plus u0 z square. Okay. u0 is another constant vector which is defined over here. Okay. So, u0 square is nothing but, if you do the calculation correctly, you will see these are nothing but square plus c2z square by 4c1 square. Okay. And then you can actually calculate the vector as well. So, u0 vectorial you will simply be minus 1 by 2 c1 c2xi plus c2y j cap plus c2z k cap. Okay. Now, finally, you can write log A is equal to c0 plus b u0 square. u0 square you now know what that is, that will be 2x square plus 2y square plus c2z square by 4c1 square. So, that will be giving A is equal to exponential c0 minus c2x square plus c2y square plus c2z square by 4c1. Okay. So, finally, we could express all the constants in terms of all the constants b, a and u0 in terms of the c's. Okay. Now, we coming back to our previous thing where we wrote that the log of f u is equal to minus b u minus u0 whole square plus log of a. If we can write that, let me just tell you one thing in case you are just lost, that here f0 is actually should be written over here. So, f0, every f should be replaced by f0 because that is only true for f0 and f0 will be there. Okay. And finally, you can say that, so log of f0 will be equal to minus b u minus u0 whole square plus log of a. Okay. If you write that, you can simply say f0 is equal to a e to the power minus b u minus u0 whole square. Okay. And that you can easily recognize, this is the famous Maxwellian distribution. Okay. Maxwellian distribution. So, finally, we could show that f0 has this form, okay. But our assumption was that only the number, the kinetic energy and the 3 components of linear momenta are conserved in binary elastic collision, okay. And f0 is a function of u only. Okay. Okay. So, here you can see that f0 basically obeys this type of distribution where a and b, these two are constants and u0 this is also a constant. Okay. So, this distribution looks very much like Maxwellian distribution, but the distribution which you have possibly encountered in the kinetic theory was not exactly looking like this, because a and b had some specific value in terms of the given characteristic quantities of the system, and also there was no u0, right. Now, we try to evaluate the Maxwellian distribution. Okay. Now, in the next step we try to evaluate these two constants. Okay. Thank you.